Hey, imagine the planet has been secretly running the most accurate stopwatch in the universe for 4.5 billion years. No batteries, no gears, no screen. Just rock, ice, and an invisible magnetic field. And the craziest part? We cracked the code. Today you're going to learn exactly how Earth records its own history, and why mastering these secret timekeepers might be the only way we survive what's coming next. Let's dive in. Most of us think in days, maybe centuries. Geologists think in millions. Hundreds of millions. They call it deep time. And the first mind blow is this: the planet writes its diary vertically, layer on layer on layer. Oldest stuff at the bottom, youngest on top. That single rule, the law of superposition, is the first geological clock. But here's the thing: the pages get folded, ripped, burned, and scattered across continents. So how do we ever put the story back together? 3 hidden timekeepers. Think of them as Earth's built-in recorders. First up, the rocks themselves. Walk up to any road cut, and you'll see stripes of different colors and textures. That's lithostratigraphy. But the real magic happens when life gets involved. Imagine you're a 19th century canal digger in England. You notice the same fossils always show up in the same order. No matter how far you dig, that's faunal succession. Evolution never runs backwards. Some creatures were perfect stopwatches. They spread across the whole planet, evolved super fast, and went extinct quickly. We call them index fossils. Best ones? Tiny plankton called foraminifera, forams for short, and the coiled squid relatives called ammonites. One handful of mud can contain thousands of these little guys, and their shells change shape every few 100,000 years. Oil companies literally steer multi-million-dollar drill bits using them in real time. Then there are global cheat codes, chemical spikes. 66 million years ago, an asteroid slammed into Mexico. It sprayed a razor-thin layer of iridium, rare on Earth. Common in asteroids, all over the planet. Find that clay layer anywhere, and you've nailed the exact moment the dinosaurs checked out. We drive a literal golden spike into the rock and say, this is the boundary. Everywhere on Earth. That's a GSSP. So rocks and fossils give us the order of the chapters. But we still need something that works the same way on every continent and under the oceans. Cue the planet's built-in tape recorder, its magnetic field. Deep in the liquid outer core, swirling iron creates a giant bar magnet. Every now and then, totally randomly, it flips. North becomes south, compasses would spin 180 degrees. When lava cools at a mid-ocean ridge, tiny magnetite crystals freeze like compass needles pointing whatever way the field was that day. New lava keeps pushing the old crust aside, so the seafloor grows symmetrical stripes, black for normal, white for reversed. Sail a ship across the ocean with a magnetometer, and you literally read the tape. That pattern is the geomagnetic polarity timescale. Match your local rock sequence to the global barcode and boom, instant age. Even if there's not a single fossil around. This is how we proved plate tectonics in the 1960s. The Vine-Matthews-Morley hypothesis predicted exactly these stripes, and when we finally looked, there they were. Mind blown. Now zoom way in, the last million years or so, where we need insane detail. Enter ice cores. Every winter, snow falls on Antarctica or Greenland. Every summer, a little more, but with slightly different chemistry and texture. Bury it under kilometers of ice, and those layers squeeze thinner and thinner, but they never quite disappear. In the top few 100 meters, you can literally count annual layers like tree rings. Deeper down, they get too thin to see, but huge volcanic eruptions leave global ash or acid spikes we can match to known dates. The deepest cores, like Epica Dome C, go back 800,000 years, perfectly dated. But here's what makes ice cores ridiculous. They trap actual ancient air. Bubbles in the ice are tiny time capsules of the atmosphere. Crush the ice in a lab, and you measure carbon dioxide from 200,000 years ago directly. The graphs are terrifyingly clear. Temperature and carbon dioxide dance together over 8 ice age cycles. They also have a built-in thermometer. Water with heavy oxygen. 18 rains out first on its journey to the poles. Colder planet equals more depleted in oxygen, 18. So the ratio in each layer tells you exact temperature. And yes, we see moments when Greenland shot up 10 to 15 degrees Celsius in a single decade. Climate can flip fast. All of this gives us sequence and correlation. But for actual calendar years, we need atomic clocks. Uranium trapped in zircon crystals decays to let at a rate so steady we can date the oldest rocks on Earth to 4.4 billion years with an error of less than 1%. Closer to us, carbon 14 dates everything organic up to about 50,000 years. Put it all together: fossils, magnetic flips, ice layers, radioactive decay, and we get the geologic timescale. A single, agreed-upon history of the planet. But here's the punchline. Earth keeps cycling. Supercontinents assemble and break up every 400 to 600 million years. Ice ages dance to orbital wobbles every 40,000 or 100,000 years. Faults rupture on semi-regular schedules. When we dig trenches across the San Andreas and carbon date the offset layers, we learn it likes to go every 300 years give or take. Guess when the last big one was? Yeah, we're overdue. Same with volcanoes. Date the old lava flows, figure out the pattern, and suddenly dormant doesn't feel so comforting. So here's the big picture. The Earth has been keeping perfect records this whole time, in rock pages, magnetic barcodes, and frozen air bubbles. We finally learned to read them. And in the Anthropocene, the age where humans are now the dominant geological force, that knowledge isn't just cool trivia. It's survival intel, because the same cycles that wrote the past are still running. And the next chapter? We're writing it right now, in plastic layers, carbon spikes, and extinction rates that will become tomorrow's index fossils. So next time you pick up a rock or see a glacier, or just look up at the sky protected by that magnetic shield, remember, the planet never stops keeping time. The question is, are we finally paying attention? If your mind is officially blown, hit that like button. Subscribe and tell me in the comments which timekeeper freaked you out the most, the flipping magnetic field, the asteroid iridium layer, or the 800,000-year air bubbles. I read every single comment. Thanks for watching, and I'll see you in deep time.